I am Arnab. I am a postdoc in Uppsala University, and importantly, following the tradition of this session, my talk is also different from the other talks. So I will be talking about quasi-periodic system in a photonic lattice, and this is a collaboration with experimentalists at Stockholm University, and the experiment is mostly done by Mohammad Buranen's group. And so basically, we have a array of waveguide and we put it in a quasi-periodic manner, and we show that if we inject light from one end of the waveguide array, it comes out from the opposite end, basically demonstrating a pumping. And so I will discuss about that. So let's begin. So as I said, I have photonic waveguide arrays, and in these photonic waveguide arrays, the propagation of light, or importantly the electric field component of light, is governed by this paraxial equation, which is nothing but Maxwell equation under this two approximation. And this equation has resemblance with the Schrodinger equation, where this electric field, amplitude of the electric field plays the role of wave function, while this propagation direction of light which plays the role of time. So once we make this connection, we can effectively model it to a tight binding Hamiltonian or tight binding chain, and in this tight binding chain we have this coupling between two neighboring sites, or the hopping term, and we have this on-site term. So this coupling depends on the separation between two waveguides, and this on-site term depends on the radius of the waveguide. So in our setup, this radius is always constant, so I will not consider this term. So I already told you about this, and in our setup we always consider two kind of distance. So dA is the longer distance, and dB is the shorter distance. So longer distance means the hopping or coupling is small, whereas shorter distance means the coupling is strong. So we use these features of this waveguide setup, and as I said, we map it to a hopping Hamiltonian, and this hopping constant depends on the separation between two waveguides, and as the separation increases, so the hopping diminishes very quickly, and as a result, in principle, one can approximate it using a nearest neighbor Hamiltonian, although for the numerical calculation this is not needed, but this is nice to motivate how we construct the system. So we have this hopping, and this hopping is not constant, so it is a function of space, and we consider it to belong to this Fibonacci sequence. So from here this quasi periodicity comes into this system, and I am just showing you the few first members of the sequence, and this sequence is constructed using this concatenation rule. Basically you sum the previous two members. Basically if you want to construct this, you just need to add these two, and here you have only two elements. You have two kind of bond, so this blue and red, and just by arranging them you can get this sequence. And there is another way one can also make this sequence via this sine function. So this sine function has these degrees of freedom called Phazon angle. So by changing Phazon angle you can generate a family of Fibonacci chain, and in this family of Fibonacci chain you can get many interesting properties, and if you want to learn more you can follow this review by Anuradha Jagannathan. So with that I just show you how the spectrum of the Hamiltonian looks as a function of this Phazon angle. I will not discuss the full spectrum, but we will focus on this red marked state. So this red marked state is a localized state depending upon the Phazon angle. So for this green marked Phazon angle, it is localized on the left, while for the orange it is localized on the right. And now if we look at how the hopping configuration looks for these two Phazon angles, so that is shown here. So we have these two configurations, and correspondingly we can make the waveguide setup just maintaining these two kind of distance dA and dB, and just orienting them according to this sequence. And the difference between these two configurations is just this, that you need to just flip 4 n bonds to go from one configuration to another configuration. So we will use this property But before that, I'll just like tell you briefly about the experimental setup. So, so in the experiment, so they fabricate the waveguide, or they call it printing, by another laser. So they have a glass bar, they move it in x and y direction, and they print the waveguide array. And once the printing is done, then the measurement is done by like injecting some light from one of the waveguide, and then they just basically capture the photo using this CCD camera, and then from there we get the intensity pattern. So now I'll go to the demonstration part. So as I said, I need to go from one configuration to another configuration. So okay, and I want to go it continuously. So in the photonic system, it is done by bending these waveguides smoothly along the light propagation direction, and then I inject light from one end, and when the pumping happens, it comes out from the opposite end. And theoretically, this bending means basically I am constructing a time evolution operator, and it is operating on some initial state and then propagating it. Here the initial state is mimicked by this single injected light from the one waveguide. And this is the result, and the theoretical and experimental result. So I am just showing you the output at this plane. So I inject light from here, and I am showing you the intensity. I am showing you the intensity output. So this is the theoretical simulation. So as we inject or light from left end, it comes out from right, and similarly in the experiment also we see that like the light is mostly pronounced on the rightmost side of the waveguide. And then we also try to study whether this pumping is robust. So we introduce some controlled structural defects. So defect is nothing but like you introduce different kind of distances in this system. So these distances are different from dA and dB. And in the presence of this structural defect, we try to see if the pumping can still be done, and we see that like it remains robust. We see that we get right localized state when we start from left localized state, and in some cases it even gets pronounced because and we saw that because it is of like increment of excitation gap that separates the pumping state from the other state. And with that, I will just summarize that I told you about this pumping in this waveguide array that one can do just by injecting light, and then you get this output light from other end. And here to do the pumping, you just need to minimally change two waveguides. So we compare it with SSH based setup. So in SSH based setup, usually if one wants to do this pumping, one has to like change all the waveguides. So in that case, we simplify this pumping. So if you want to know more, so you can take a look at our articles. Thank you.
Introduction. I know about Thouless pumping where electron is integer electron is transferred. So is there any similarity? Can you use it for photon transfer, single photon rather than a wave property?
Here we basically utilize the classical photon. Yeah, and it is different from Thouless pumping, because in Thouless pumping you want this initial and final Hamiltonian to be same, so that you have quantized charge pumping, but here it is not that. Yeah. Yeah.
So you got this edge modes.
Yes.
In case. So my question is like the topological invariant that we see, is it a usual churn number or it is different?
Well, this system has some topology, but not the 1D version. So this phasonic degrees of freedom I was telling about, if you combine that with the physical dimension of the system, then you can compute churn number for different quasi-periodic gap the system shows. But on its own, the 1D system, some people call it topological, but there are some works that showed that it is on its own is not topological, but it has some protection from its parent 2D system.
Okay.
Yeah.
Any other question?
Hello everyone, I hope I am audible. I am Santanu, I am from Indian Institute of Technology, Bombay. I am working as a National Postdoctoral Fellow there in the lab of Professor Hridish Kumar Pal. This talk is based on our recent publication in Physical Review B, and the title of this talk is Chiral Anomaly in Spin-1 Fermionic Systems. So, in this talk we are going to talk about chiral anomaly in systems where Lorentz symmetry is absent in comparison to wild semimetals where there is some emergent Lorentz symmetry. So, let us briefly discuss a few points on wild semimetals, and then we quickly move into the other kind of materials that we want to talk about. So, wild semimetals are materials which realize this kind of discrete band touching points. They appear in pairs always, and they have equal and opposite topological charges defined through the integral of the Berry curvature over a surface surrounding these nodes in the Brillouin zone. And now, if one expands the tight binding Hamiltonian around these nodes, the excitations of the Hamiltonian comes about something like sigma dot k, and the total Hamiltonian considering both the nodes is written as shown here. Now, one can try to construct an effective field theory from this Hamiltonian, and this effective field theory is exactly that of wild fermions as it is encountered in the context of particle physics, and therefore it has a emergent Lorentz symmetry, and this effective field theory also reveals other emergent symmetries, like there is a chiral symmetry also present, which is basically the symmetry of this Lagrangian by the transformation of these wild spinors by opposite phases, and this gives rise to a conserved chiral current, and now that is only the classical conservation, and so one can try to consider quantum effects, and one can show that under quantum effects this conservation gets violated, and that is what we called chiral anomaly in this context. So, in the condensed matter context, chiral anomaly is often expressed by this equation, which is basically the charge conservation equation at a given node k. And as we can see that in the right hand side there appears a term which shows that in presence of parallel electric and magnetic field, the charge conservation at a given node violates, and the degree of violation is proportional to the topological charge of the node. So, this relation is derived in the condensed matter context using semi-classical equations. However, here we are going to consider fully field theoretic method, which is path integral based field theoretic method, which is called a Fujikawa method, and in this method one considered the transformation of the fermionic spinors by the chiral phase, and consider how the path integral measure changes under this transformation, and this Jacobian of this transformation gives rise to this form, which is exactly same as E dot B. Now, it seems that as this number is topologically quantized, it seems that for every topologically non-trivial node will give rise to a quantized anomaly coefficient. However, as we shall show in next few slides that this is not the case. In fact, there can be systems like these which some of which, I mean all of them have non-trivial topology and they are higher than 1, but some of them violates this emergent Lorentz symmetry, and we are going to consider this kind of systems in our work. So here we consider specifically this spin 1 excitation. This is basically pseudo spin 1 excitation, and the Hamiltonian of this excitation is given by this 3×3 Hamiltonian, and the corresponding dispersion is shown here. So as we can see, there are two linearly dispersing band and another is flat band. These linearly dispersing bands are topologically non-trivial, they carry charges plus minus 2, and the flat band is topologically trivial. Now we want to ask the question that what happens to the chiral anomaly, that is the charge conservation equation at each node for these kind of systems. Now in answering that question, one first gets the difficulty that faces the difficulty that the chirality operator in this case, and therefore the chiral symmetry is not properly defined for these odd dimensional spinors. Therefore, one can try to think how to reformulate this spin 1 fermion in terms of even dimensional relativistic type spinors. So one gets the first hint from this type of band structure, which actually appears in real systems like RHSI, where spin 1 appears with a 2-flavor while, and one can thus think of that this spin 1 fermion along with this higher band might have appeared due to some kind of hybridization due to some potential, and this is schematically shown here. This is a 2-flavor while fermion. Okay, this is the 2-flavor while fermion which have the Lorentz symmetry, and one can break Lorentz symmetry by adding a Lorentz symmetry violating potential, and that will give rise to this 3×3 band structure along with this higher band. Now in calculation we implement it like this. We start from the 2-flavor while, then convert it to the change the basis to triplet singlet basis in the spin flavor space, and we see that a spin 1 type Hamiltonian has appeared. Now one can try to add some Lorentz violating terms like this to obtain the this kind of Hamiltonian. This can be further generalized, and by scaling this factor by g, and that would only change the dispersion of these flat bands to a general dispersing bands. And now one can express this Lorentz violating potential in terms of some non-abelian potential whose components are given by this. Now one can consider the situation where both the nodes are spanned by spin 1 fermion. One can construct the effective field theory from the previous one, from the previous Hamiltonian that we get here, and calculate the corresponding charge conservation equation for a given node. And here we see that one gets the topological term which is exactly same as previous contribution from topological consideration. However, we also get one another term which comes purely from the Lorentz violating potential, and this varies continuously when we vary g continuously. Therefore, this is a non-topological term. And we also have done the same calculation for spin 1 2-while system, which is actually the realistic system, and here we see similar term appears with a factor of half. Now this can be captured, this g dependence can be captured by calculating the longitudinal magnetic resistance, and here for while it is 2 for 2-flavor while, it deviates from 2 by some g dependent factor in both cases, and that is captured here. So finally we can say that the emergent Lorentz symmetry may lead to non-quantized anomaly coefficient, and it will have effects on longitudinal magnetic resistance. So these are the future works that we are planning. I would like to acknowledge the contributions and guidance of Professor Hivish Kumar Pal, who is my mentor, and also Professor Sanjana Sharma, who is our collaborator from IMSC. I would also like to thank organizers and the audience. Thank you for your attention.
Have you checked so when you are defining a 3/3 Hamiltonian and presumably for spin 1, the time universal symmetry definition changes. So have you looked at what sort of, when you say time universal symmetry breaking while and all, it has to be redefined. The chiral anomaly also
For
has to be,
no, we have not checked it.
you can't have a Kramer's degeneration, all these things.
No, this type of thing, spin 1 fermions, they appear in real systems. So it's not a postulated system.
All right. Yeah. Thank you.
Okay, so hello everyone, welcome to my talk. I am Amulya Ratnakar, postdoc at CNRS Marseille, and the topic of my talk is on the effect of inter-edge interactions on the braiding phase of anyons in a quantum Hall collider setup. To start with, I would like to start with a small introduction to anyons, and then some recent experiments in in finding the fractional statistics of anyons. And then I'll come to my work later, and then results and conclusions. Okay, to start with anyons. So anyons are the particles which interpolate between bosons and fermions in the sense that they have fractional charge and fractional statistics. Fractional statistics as in if you take anyon around another, it gains a phase which is which does not corresponds to bosons or fermions. It is somewhere in between. And these particles exist as the fundamental excitations in a fractional quantum Hall state. The fractional charge has been detected decades back, but for fractional statistics, the work is still ongoing, and there has been a very small number of experiments which deals with the direct evidences of fractional statistics. And these experiments depends on the interferometer setups or collider setups. So in an interfero setup like Fabry-Perot experiments, we have the spatial braiding of edge anyons with the bulk anyons, and the phase and the interference depends on the exchange phase of these anyons at the edge and anyons in the bulk. However, in a collider setup, we do not have the spatial braiding of the anyons, but what we have is something called time domain braiding, which I will explain here. So in a typical collider setup, what we have is two source QPCs which inject anyons across the bulk, and a central QPC where these injected anyons come and time domain braid at the central QPC with the quasi-particle quasi-Hall pairs that are created at the central QPCs. And what is time domain braiding? So time domain braiding essentially is the convolution of two processes, where in the first process these injected anyons reach the central QPC after the quasi-particle quasi-Hall pair has been created, and the other process is when these injected anyons reach the central QPC before the quasi-particle quasi-Hall pair is created. And the time domain and the convolution of these two processes will give you the braiding of these injected anyons with the quasi-particle quasi-Hall pair in the time domain. And then you will get a phase which is delta, which is the total phase of the braiding, total braiding phase of these injected anyons with the quasi-particle quasi-Hall pair at the central QPC. Okay, so in a standard collider experiment, what we measure is the normalized cross correlation, and we call it a P factor, and it is in good agreement with the for Laughlin filling fraction. It is it is in good agreement with the experimental finding which is given by this. But when we have like multiple edge modes at the boundary, then for example in a nu equal to 2/5 state, for a charge of q equal to 1/5 and a scaling dimension of 3/5, the theoretical prediction is to have the p value at 6. But what we get essentially is the p value to be -1, and this is in total disagreement with the theoretical prediction. So we would try, what we did is to try to address this discrepancy by taking into account the inter-edge interactions between the two edge modes in an equal to 2/5. So before going forward, I would first start with the nu equal to 2/5 edge structure. So in a nu equal to 2/5 quantum Hall state, what we have is two edge modes, with the outer edge mode having the conductance of 1/3 and the inner edge mode having the conductance of 1/15. And any quasi-particle operator at the edge can be written as this, where in terms of, and it can be expressed in terms of bosonic field using the bosonization technique, where G alpha is the vector which defines the property of the quasi-particle at the edge. So the most probable type of anyons in a 2/5 is, let's say, type 1 and type 2 anyons, which are given by these two G vectors. And this G1 anion only lives on the innermost edge, and this G2 anion lives on in both the edges. And they have the same scaling dimension, which is given by 3/5, and they have the same exchange phase, which is given by 3/5 also, and the same charge, which is given by 1/5. Okay, so now we can write the interacting edge Hamiltonian in terms of bosonic field, which is given by this, where lambda is the interaction strength. And if we do that, and if we let's say diagonalize the Hamiltonian, then what we get is the normalized velocities along the edge modes, and at the central QPC, what we have is the tunneling Hamiltonian, where gamma is the tunneling strength corresponding to the alpha type of anion. Okay, now let's say if 2 minutes. Okay. So now let's say if we have control over the injection process at the source QPCs, and we inject let's say type 1 or type 2 anions, so we get the tunneling current expectation value, something like this, where this lambda is the braiding phase of the injected anions with the quasi-particle quasi-hole pair at the central QPC. And if we look at the structure of this braiding phase, so if you like TL minus L by Vg is the time taken by this injected anions to reach the central QPC, and if this along the eigenmodes, and if this time falls between T and T prime or T1, it picks up the phase which is given by G tilde gamma and G tilde alpha along the jth eigenmode. Otherwise, this is 0. So, and you can see it here in this graph very well. So, let's say in the absence of any interaction where lambda is 0, you see that for both the type of G1 and G2 anions which are injected at the source QPC, you do not have any discerning differences between the tunneling currents. But as soon as you switch on the interactions, so at this point, the faster anion along the eigenmode hits the central QPC first, and then there is a power law decay due to the green function, and then the second anion along the slower eigenmodes come and hits the central QPC, and then at the long time interval, both the behavior of the tunneling current is same. Now, in general, we do not have the handle on the injection process, and the injection process at the source QPC in general is Poissonian in average, and what we do is the Poissonian averaging over the injection time of the anions. And if we do that and we calculate the expectation value of the tunneling current, what we get is this very messy, however, an intuitive expression. And if you see that this expression is divided into two time domains, where t is greater than delta tau and t is less than delta tau. For t greater than delta tau, we have this sort of braiding phase contributions, where this and this phase corresponds to the uncorrelated part of the anion beam, and this uncorrelated part of the anion beam gives a phase which is interaction dependent. However, in the time domain, let's say t minus delta tau, we have the phase which does not depend on the interactions. But in the, it's just finishing, it's the last slide. Okay. So, but in the time domain where t is less than delta tau, we have the phase which depends on the interaction, and this is the limit when we have the long junction limit. And this is the final slides for my results. So, so let's say in the
Go to the conclusion. Your time is up. Your 10 minutes is up.
okay, so this is the conclusion.
If there is no. Otherwise, explanation.
You heard about edge reconstruction in quantum states.
Mm-hmm.
So instead of assuming interaction between edge states which are overlapping spatially, suppose there is an edge reconstruction.
Okay.
Can you explain some of these phenomena?
Okay, so this approach can be extended to like having multiple edge modes, and this includes the edge reconstruction scenario that we have. Like for an n equal to 2/3, we can have multiple edge mode structures, and then I guess the result would change according to the edge structure that we can take.
Even for two, can't you imagine edge reconstruction?
Yes, so here for 2/5, one of the possibilities is having this sort of edge structure, and yeah.
Because kind of up, but if you want to say one or two more for your conclusion.
Okay, so I'll just explain the key points. No.
Go ahead.
All right. So okay. So the main point is that in the absence of interaction, you get the p-value, which is something like 6, which is the theoretical prediction. But as soon as you increase the interaction, you shift from, let's say, positive values of p to the negative value, and subsequently come to the experimentally found regime, which is closer to -1, and correspondingly you see the change in the tunneling current sign from negative to the positive. So this is what which exactly matches with the experimental findings. Thank you.